Okay, so good morning. Good morning, class. Welcome back. Welcome back to my subject, Logic Circuits and Switching Theory. We are now in the fifth session with the topic binary code. So we have several binary codes actually. So we have ASCII, EBCDIC, and we also have, we're going to tackle three of those. So we have binary coded decimal, one, XS3 here, and gray code. Okay, but if you want to know more about binary code, so you can take a look at Logic Circuits by Morris Mano as a reference. Okay, so let's start. So binary codes, or first one of binary codes that we're going to tackle is the binary coded decimal, or BCD. So each decimal digit is represented by a 4-bit binary. So example here. So we all know that decimal bit or decimal digit is 0 to 9. Those are the valid symbols. So each digit in decimal should be represented by 4 bits in BCD. For example, so you have 0 here. It should be represented by 0, 0, 0, 0. It should be 4. So for 1, so it should be 0, 0, 0, 1. For 2, 0, 0, 1, 0. For 3, you have 0011. For 4, we have 0100. For 5, we have 0101. 6, 0110. 7, 0111. 8, 1000. 9, 1001. So example here. So if we have 123 in base 10, so in BCD, it should be represented by 0001, 0010, and 0011. So each digit in decimal again should be represented by 4 bits in BCD. Next, so what if we have 406 here? Given is 406 in base 10. So how are we going to represent that in BCD? So in BCD, so 4 is 0100, 0 is 0000, and 6 is 0110. So just take note that each digit in base 10 should be represented by 4 bits in binary in BCD. So always 4 bits. Okay. Next, we have XS3. So XS3 is BCD plus 3, such that let's take a look. Let's have a comparison here. Table 1.3. Okay. So let's say you have 0 in BC, that is 0, 0, 0, but in XS3 plus 3, that is actually equivalent to 0, 0, 1, 1. Okay. And then for 1, so you have 0, 100. For 2, in XS3 is 0101. For 3, that is 0110. For 4, that is 0111. 5 is 1000. 6 is 1001. 7 is 1010. 8 is 1011. And 9 is 1100. Okay? So it's actually plus 3. So take note. 9 plus 3 is 12. So if we're going to add this, okay, so the weight of the first bit is 1, the weight of the second bit is 2, the weight of third bit is 4, the weight of fourth bit is 8. So we're going to count the weight of bit with bit for bit when bit is equal to 1. Okay, we're going to add the weight when bit is equal to 1. So example here, 1100. So 8 plus 4 is 12. Okay, because 9 plus 3 is 12. Okay, so that's the equivalent of 9 in XS3. 9 plus 3 is 12, so therefore it is represented by 1100. How about here? 8. 8 plus 3 is 11. Okay, so we have, is this 11? So we have 1 plus 2, 3 plus 8, so this 11. For 7, 7 plus 3 is 10. So let's count, let's add. Okay, let's add the weight when bit is equal to 1. So we have here 2 plus 8. So we have 10. For 6, we have 6 plus 3 is 9. So we have 1 plus 8 is 9. Okay. 5 plus 3 is 8. So we have 8 here. Okay. For 4 plus 3 is 7. So we have 1 plus 2 is 3. 1 plus 2 plus 4 is 7. 1 plus 2 plus 4 is 7. Then for 3 plus 3 is 6. So we have 2 plus 4 is 6. And for 2, we have 2 plus 3 is 5. So we have 1 plus 4 is 5. And 1 plus 3 is 4. So we have 4 here. And last, you have 0 plus 3 is 1 plus 2. So we have 3. So those are the equivalent of x is 3. So actually, you don't have to memorize. You just have to familiarize yourself with this. So again, so each digit in decimal should be represented by 4 bits in x is 3. Example here. Same given. So how do you represent 123 in base 10 to x is 3? So we have for 1, so you have 0, 100. For 2, 0, 1, 0, 1. For 3, it is 0, 1, 1, 0. So that's how you're going to represent 123 in base 10 to x is 3. Okay. How about 965? So 965 is represented by 1100. For 9, 6 is 1001, and 5 is 1000 in x is 3. Okay. So I hope everything's clear. Okay. And last, we have gray code. Okay. We have gray code. So gray code is generated when adjacent bits starting from the least significant bit. So the first bit is the least significant bit is inputted to an XOR gate. So the most significant bit is copied. So kinokopya lang natin the MSB here. So example, convert 1000 base to gray code. So conversion to gray code is done. Okay, so it should be base to BCD. Okay, so example here given is 1000 in binary or BCD. So are going to convert that into gray code. Okay, so let's see. So given is 1000. So the plus here, plus sign inside the circle. So actually that's the symbol for operator symbol for XOR, operator symbol for XOR, because you have AND is multiplication, so it can be represented by dot, or is plus. Okay, but if you have plus inside the circle, so that is XOR. So if you have dot inside the circle, that is XNOR. Okay. Okay, so this is XOR, so that's why we have plus inside the circle. So again, that is the operator symbol for XOR. Okay, so we have 0 XOR 0. So the thing with XOR is that it generates an output of 0 if both inputs are equal. So let's say both 0, so the output is 0. If the inputs are both 1, the output is 0. Okay, so if the inputs are different, so let's say 0 and 1, so that's when it will generate an output of 1. Okay, so let's see. Okay, 0 XOR 0, so we have an output of 0 here. Next, 0 XOR 0, the output is 0. Okay. 0 XOR 1, the output is 1. And then you copy the MSB. So you just bring it down here. So therefore, 1000 is equivalent to 1100 in gray code. That's how you generate the gray code. Gray code, binary usually is being transformed to gray codes because gray codes generates the least change in bits. Okay, so it's actually generate 1 bit at a time for 0 to 9 here. Okay, so following the methods here, so we're able to generate these gray codes here. Okay, for 0 to 9, we have equivalent gray code here. So again, the gray code here is based on the binary here. So let's see. 0 XOR 0 is 0, 0 XOR 0 is 0, 0 XOR 0 is 0, and then you bring down the MSB. That's why 0, 0, 0 in BCD is also 0, 0, 0 in gray code. Okay, so how about this one, the gray code of 0, 0, 0, 1. Okay, 1 XOR 0 is 1, 0 XOR 0 is 0, 0 XOR 0 is 0, and then bring down 0. So we have it here. Okay. Next, 0, 0, 10. Okay. 0 XOR 1 is 1. Okay. So you have the first answer here. 1 XOR 0 is 1. Okay. Okay. And then we have 0 XOR 0 is 0. And then bring down the most significant bit, 0 here. So that's how. So therefore, the equivalent of 0010 in BCD is 0011 in gray code. Next, 0011. So 1 XOR 1 is 0. Then 1 XOR 0 is 1. Okay, so we have 1 here. And then 0 XOR 0 is 0. Okay, so you have the third bit as 0. And then bring down 0. Okay, so therefore the equivalent of 0011 in gray code is 0010. Next is 0100. So 0 XOR 0 is 0. Okay, then 0 XOR 1 is 1. Okay, and then 1 XOR 0 is also 1. Okay, and then bring down 0. For number 5, okay, 0101. So 1 XOR 0 is 1 XOR 0 is 1. Okay, next bit, 0 XOR 1 is also 1. Okay, 1 XOR 0 is 1. Okay, so we have 1 here. And bring down 0. Okay, next, 0110. 0 XOR 1 is 1. Okay, then 1 XOR 1, okay, is 0. Okay, and then 1 XOR 0 is 1. Okay, and then bring down 0. Okay, and then next we have 1 XOR 1, okay, is 0. Then 1 XOR 1 is also 0. Okay, next is 1 XOR 0 is 1. Okay, that's why we have 1 here. And bring down 0. Okay, for 8, we have 0 XOR 0 is 0. Then another 0 XOR 0 is 0. And then 0 XOR 1 is 1. Okay, and then bring down 1. And last we have for 1001. Okay, 1 XOR 0 is 1. And then 0 XOR 0 is 0. 0 XOR 1 is 1. And then bring down 1. Okay, so that's it. So that's how we generated this gray code here. So take note that gray code poses a minimal bit change. So take note, from 0 to 1, we only have this bit that changes. Okay, so there's only one bit change. So from 1 to 2, you only have the third bit that changes from 0 to 1. And then from 2 to 3, we have the first bit. Okay, so we have this bit that changes from 1 to 0, this one. Okay, so we have the third bit that changes from 0 to 1, and then we have, okay, from 4 to 5, so we have this bit that changes from 0 to 1. Okay, so from 5 to 6, we have this bit that changes from 1 to 0. From 6 to 7, we have this first bit that changes from 1 to 0. And then from 7 to 8, we have the fourth bit that changes from 0 to 1. And for 8 to 9, we have the first bit from 0 to 1. So that's why gray code is often used in digital techniques. Okay, so because you only have a minimal bit change. Okay. Minimum bit change. Okay, so that's it for now. Okay, so we have finished chapter 1. Yes. We're done, class. Very good. Good job. So I hope you understand everything. Okay, so I'm going to resend these instructional materials as we have discovered some typo errors. Okay, some typo errors, and then I'm going to reload this in MS Teams. And then you have a new assignment, so binary codes. Okay, so we have for A given is decimal, so you have to convert it to BCD, XS3, and gray code. And then for B, we have from BCD, then convert it to decimal, XS3, and gray code. And last, we have the given is in XS3, then you have to convert that into BCD, decimal, and then gray code. Okay, so in doing your assignment, so if possible, so may print this page. Okay, or you may just what do you call this, edit this one and then give it back to me. Just don't forget to write your name, please. Or if you have to handwrite the you have to write your assignment in handwriting. Okay, you have to do it handwritten assignment, so please write in a bond paper. Okay, bond paper na clean white paper. Okay, so it would be easier to see, it would be easier to check, it would be easier to view. Okay, so that's it for now. Okay, we're done. So next week we're going to have your first unit exam and chapter 2. So we're now in chapter 2. Okay, so for now, so stay safe everyone. So bye.